we've gone through the details of a couple of examples of the basic idea behind arithmetic coding. And so far we've been assuming infinite precision. That is, assuming that we can do addition and multiplication exactly with infinite precision. Now, soon we're going to write down the general algorithm of how to do arithmetic coding in the infinite precision case. And then later we'll see how to turn this into a practical algorithm that uses only finite precision. That's of course necessary for anything you're going to implement on the computer. But the infinite precision version is easier to understand, so we'll do that first. Now, there's multiple ways that you could implement the infinite precision algorithm, but I'm going to do it in a way that introduces certain concepts that will be important later on when we look at the finite precision case. So the important concept that I'd like you to start getting your head wrapped around is rescaling. So let's go back to example 1 here. This was our first example. And let's think about this. So the part 1 was finding the interval from a to b, and let's keep that the same. But let's think about part 2 here in a little bit of a different way. So in part 2, conceptual part 2, we were subdividing the interval from 0 to 1 into these binary splits. And we were doing so in such a way that finally we would end up with a chunk that was completely contained in the 2, 1, 0 chunk in this a to b interval. And so let's visualize this in a slightly different way. So I'm going to turn this interval on its side and draw this process involving certain rescaling operations. So let's take this interval from 0 to 1 and this a to b subinterval, and let's draw that down here. So we have here, let me make it a little skinnier, actually. Skinnier. So this is our interval now from 0 up to 1, and the interval from a to b, and so we're going to split this in half. That's, it's roughly half there. And the interval from a to b is roughly, what was it? It was like 0.68 to 0.712, somewhere around there. A to b. All right. So let's visualize this process in the following way. So the first step was we were going to subdivide the upper chunk. So this was the 0 chunk and this was the 1 chunk, and we were going to subdivide the 1 chunk. But rather than do it in place here, let me rescale this back out to a full interval. So this is, I'm going to take the 1 chunk and blow it up. So maybe I'll draw it twice the width, so that it's sort of visualized, so you can visualize this as sort of coming out of the page. So this is split again. This is now we're going to have a new 0 and a new 1. And this goes back to here. This comes from here. And the a to b goes to roughly, I don't know, somewhere around here. It's going to be twice the width of that. So maybe I'll try to do things to scale. So that's where a to b goes to. A, b. And now, so the first symbol then, we can just see right off the bat that the first symbol is going to be a 1. So we could say here, we could just make a note of that. We'll put 1. And at the next step, we're going to subdivide the 0 chunk. And let's visualize that in the same way. Let's blow up, instead of just subdividing it, let's blow it up back to a full sort of interval length. So we're just visualizing this in a different way. This comes from here. And where does AB go? AB goes, let's see. Well, let's first finish drawing our, so this is it's going to split there. We're going to have a new 0 and a new 1. And A to B goes, it goes somewhere around, I don't know, here. It's twice the width now. So this is our new A, and this is our new B. B. And now we just keep doing the same thing. And so at that step, we note that we're going to have a 0. So let's write 0 to note that. And now we keep going. So let's say, so now we're in one world. So we're gonna blow up the upper chunk. I'm drawing these thicker and thicker so you can visualize a sort of staircase coming down here. So this is sort of a staircase coming down, if you can see that. So now we're going from here, and we split once again, 0, 1, and where does A, B go? A and B go. Now they're going to contain, oops, let's make that red for consistency. Now they're going to contain this half point, and that's significant. This is A, this is our new A, and this is our new B. So now we have to do something slightly different. So, well, first we knew, so this was going to be a 1. We know that, so we could go ahead and write that down. And now something different happens, right? Remember that we're subdividing until we find a binary chunk that is contained completely within this A to B chunk. And so at this step in the process, so here we're at the corresponding thing. So this number right here, or the number that sort of corresponds to this midpoint, would be, so we have 101, and that would be another 1. So that would be like 1011 in binary, which is, so we're now at the same point in the process as we were right here when we were at this step. So we had a 1, and then a 0, and then a 1, and now we have a number that's contained in that A to B interval. And then we had to subdivide a couple more times to get something that was to get a chunk that was fully contained. So here, what's going to happen is that, so what you can visually see it already here. The first binary chunk that's going to be contained, it's not going to be, you know, if we were to divide at the 3/4 point here, that's not going to be fully contained. We would have to go one more and divide at the sort of 1/2 to 5/8 this piece right here. So in order to represent how we're going to do that, let's rescale this in a slightly different way. Let's maybe make a, I'll put it right here. I'll denote, if we were to split this guy in quarters, this would be 0, 0, 0, 1, 1, 0, 1, 1. And now let's blow it up. Let's blow up the middle half, sort of here, because that's where A and B are. So that's the part we care about, right? Let me make some space. Getting bigger and bigger here because we're coming out of the page visually, and these chunks are getting blown up. So now we're gonna blow up this middle half right here. So this piece, and where does A and B go? Well, we can draw our half stays put, comes from right there. A and B go. A, this is A, this is B. A goes somewhere, oops, that's not a good line. A goes somewhere around here, and B goes somewhere way over here. Something like that. So this is our new A, this is our new B, and now we're looking like we're in pretty good shape, because now what we can do, so this one, this piece right here, this is sort of like a 0, 1, right? This came from the 0, 1 part. This is the 1, 0 part. And if we divide this one more time into quarters, like this, then we have a 0, 1, 0, 0, 1, 1, 1, 0, 0, and a 1, 0, 1 part. And the 1, 0, 0 chunk, this little chunk right here, is fully contained in A to B. So we did this sort of middle rescaling thing, and we kept track sort of what was going on there. And then we noted that after doing that, we could take this this sort of middle upper quarter and use that. That was contained in a to b. So back to, so our final thing here is going to be 1, 0, 0. So we have 1, 0, 0. So all together, we had 1 was our first. We were in the upper half. We had 1, 0, 1. And then at last, the last step, we had a 1, 0, 0 right here. And that agrees with the original thing, right? Back to the original, the other way we did it, we also had 1, 0, 1, 1, 0, 0. So this is just another way of visualizing what was going on. Now, if you think about it, in any case, in any situation that arises, no matter what A and B are, what's going to happen? Well, it's going to start out in either, maybe it'll either be in the lower half or the upper half, or it's going to straddle the midpoint. And so if it's in the lower half or the upper half, then we're going to have some sequence of, we're going to have some sequence of 1s and 0s. Like in this case, we're going to have, a 1 and then a 0. So as long as it's in either the lower half or the upper half, then we're going to be bouncing back and forth between these 0 and 1 case. I mean, maybe we'll stay in 1, 1, 1 for a while, and then 0 for a while, and then we'll switch and so forth. And then, but as soon as A to B straddles the midpoint, then we don't have any of more of the previous cases because we're only expanding this middle sort of chunk, the middle sort of half at each step. And with that sort of rescaling, the midpoint stays right where it is, and A gets smaller and B gets bigger. So we're going to have some sequence of these first sort of steps, these 0 and 1 steps, and then we're going to have some sequence of this sort of middle expansion steps. And then we're going to finally end up with being in either the upper, the third quarter, or sort of the second quarter. And if you think about it for a minute, at that last, for this last sequence that we have to write down, it's always going to be either 1, 0, 0, 0, some number of zeros, or 0, 1, 1, 1, 1, 1, some number of zeros, some number of ones, excuse me. So it'll be 1 and a bunch of zeros, or 0 and a bunch of ones. And the number of zeros or ones is going to be the number, it's going to be 1 more than the number of times that we expanded the middle half. Here we expanded the middle half 1 time, and we had 2 zeros. So that's going to, in general, if you think about it, that's always going to be the case. It's going to be 1 more, 0 in this case, than the number of times you expanded the middle half. And so you could just count how many times you do that operation, and then when you finally figure out if you're in the third quarter or the second quarter, then you write down the correct sequence. Okay, now I'd like to distinguish and sort of arithmetically write down some algebraic operations that describe these rescaling things, and those are going to show up in our in the algorithm for the infinite precision algorithm that we write down, and they will be crucial in the finite precision algorithm that we write down. So let's break out these different operations and write them down algebraically. So the first one here, actually let's do this. Let's think about this case first. So the 0 when we're in the lower half first. So we could write down. Let's call this case 0. In case 0, we have b less than 1/2. And what do we do? Well, let's draw the picture just to remind ourselves. Actually, let me do it in the same. Let me do blue to distinguish. Okay, so in this case, we're in the following situation. We have A and B are somewhere down here. Who knows where they are? But B is less than 1/2. So here we have case 0, B less than 1/2. Oh, blue. less than 1/2. And what do we do? What we're going to do is we know that we're going to have a 0. This is 0 or 1. So we say, let's say emit 0. I'm going to say emit to mean that that's going to be the next sequence in your encoded, or rather the next symbol in your encoded sequence. So in case 0, it looks like this, and we do the following. We emit 0. And what happens to A and B? Well, A, you know, what happened up here, remember? So here, we just blew up this 0 chunk to a full interval, this 0/2. So in other words, we just multiplied everything by 2. So here we just say A becomes 2A and B becomes 2B. I'm just going to use equal sign. Well, maybe I'll put colon equals. I'll put colon equals to say sort of algorithmically that A gets assigned to the value 2 times A. And the new B is 2 times B. Okay, I think you get the point. And now what's the second case? Let's call this case 1. In case 1, A is greater than 1/2. So the picture here was what happened the first time. Try to draw things reasonably well. So here we have, again, 0 and 1. This was 0 and 1. And now A and B, the interval from A to B is somewhere up here. Who knows where? Somewhere up here. A to B. And so in this type of rescaling, we say, well, we know that the symbol was a 1 because we're in the 1 part, so we may as well say emit 1, and then we're going to rescale in the following way. We're going to remember what happened up here, this one. So we sort of blew up the 1 chunk, the upper half, and algebraically we could represent that as saying, well, just subtract 1/2, move it over, and then multiply by 2. So this is just A becomes 2 times A minus 1/2, and B becomes 2 times B minus 1/2. All right, and now, so those are the first 2 cases. And now how about this middle half case where we blow up the middle? So in this case, let's call this case S for splitting the middle. So in this case, we have 1/4 less than A, and A is less than 1/2, and B is greater or equal to 1/2, and less than 3/4. So the picture here is the following. I think you can see the picture, but let's draw it just for reference at least. So we have, let's draw the 1/4 and 3/4 points now. So in this situation, A and B are somewhere. A is bigger than 1/4 and it's less than 1/2, so it's somewhere over here. And B is somewhere maybe here. A and B. And in this situation, what we do is we aren't going to emit anything because we don't know what the final thing is going to be. Remember, it could have either been, once we got to this stage, the final thing could have either been 0 and then a bunch of 1s, or 1 and a bunch of 0s, and we don't know which one it's going to be. But in order to keep track of how many times we do this operation, let's keep a counter. So let's count the number of times and let's increment it. Let's say our counter is S. So we'll increment that counter, and we will do the following rescaling. Well, we're going to blow up the middle half. So what does that correspond to? That corresponds to subtracting 1/4 and then multiplying by 2. So A becomes 2A minus 1/4, and B becomes 2B minus 1/4. And then at the last step, so maybe I'll write the last sort of possibilities are the following. Maybe I'll call them 3Q and Q for the 3rd quarter or the 2nd quarter, or maybe 2. I'll just Q. So the third quarter situation is what happens when we have a less or equal to a half, and b greater or equal to 3/4. So I'll put it this way. This is the situation where what happened here. B was greater or equal to 3/4, and a was less or equal to a half. And the other possibility that could happen is that it's the symmetric thing. A is less or equal to 1/4, and b is greater or equal to a half. So let's just draw those, and then we'll be in very good shape for the algorithm. So this is, we need our quarters again. 1/4, half, 3/4. So this guy is A is somewhere here and B is somewhere here. This guy, A is somewhere here and B is somewhere here. It could be bigger also. B could be up here, but let me put it here just to make it clear. So in this in this third quarter case, we're going to choose this third quarter. And what that corresponds to is we're going to increment our counter one more time, and then we're going to emit the last bits in our sequence are going to be 1 and a bunch of zeros. So 1, 0, 0, 0. So this is S zeros. Remember? Because up here we had we did this one time, so at this point this amounted to incrementing S by 1 from it starts out at 0. We incremented it by 1, and then at the last step we say increment it once more, and we emit 1 and 2 zeros because at this point S is equal to 2. And then we're done at that point if that case occurred. And in the other case we would do the symmetric thing. Increment S and then emit 0 and S1s. S1s. Okay. And of course, this one occurs when we choose this lower quarter. Now, it could happen that B is also greater than, so A is less or equal to 1/4, and B is greater or equal to 3/4. And in that case, you could choose either the second quarter or the third quarter, and both of them would be valid choices. But you can just pick one. So these are sort of the key algorithmic steps that are going to occur in our algorithm that we're going to write down, at least for the conceptual second part of the algorithm. And so hopefully by going through this and explicitly breaking these up, this will make it easier for you to understand the algorithm when we write it down.